Lecture 10. Yesterday we started talking about how we are going to characterize a sample and hold when you actually design one in simulation, and what we concluded was we need to make the input tone and the reference tone, okay, be related by a fraction. That is, you want to make Fn by Fs of the form small m by capital M. M is called the record length, because if this relationship is valid, then you will find that the discrete time sequence obtained by sampling the periodic continuous time input also happens to be periodic, in which case you can compute its discrete Fourier series using the FFT. Alright, and we also saw that since this is an m point sequence, the discrete time Fourier series or the FFT will also be an m point sequence, and for a real input signal, which is what we have, there will be conjugate symmetry in the FFT, and what are of relevance are therefore only one half of the DFT point. If we were not careful in choosing Fn, that is, in spite of choosing Fn by Fs to be a rational number like this, if we were not careful in choosing this rational number properly, then we could definitely end up in a situation where harmonics of the input will alias back onto the same frequency bins as the fundament. Okay, a case in point being when the input tone is at Fs by 4 and you sample it at Fs and you found that all odd harmonics will alias back onto Fs by 4, thereby leading you to conclude incorrectly that the sample and hold is perfect, right, whereas in reality it could be distorting terribly. You understand? So a safe strategy to do that would be to choose M to be, as I said, M is typically chosen to be a power of 2, some 2 to the power, I don't know, n or something. And the reason why it's chosen to be a power of 2 is simply to facilitate the fast computation of the discrete Fourier series. And in our kind of situation, it's only, I think, now mostly ornamental value, because there's nothing, these FFTs can be, with the kind of processing we have today, computing 1024 or 36,000 point FFTs are all done in a jiffy, so it's not really that big of a deal. And M is chosen to be a prime number in the region where you want to put the input. It's not strictly necessary for M to be an absolute prime number. All that it has to be is, it has to be relatively prime with respect to M. Okay. So this is what we do in simulation. The next question is, what should we do in practice? So please note that when you are testing a sample and hold in the lab, you have a sample and hold, you need to supply it with an input tone as well as a sampling clock. And if you want to be able to do this, then what constraints must be there on these two sources? You understand? The question I'm asking you is, so this is your black box sample and hold that you are planning to test. Okay? So the output samples are coming like this. You will take these samples somehow into MATLAB and do FFT. But this requires a sampling clock Fs as well as an input sinusoid with a frequency Fin. And we just said that if Fin and Fs are not related to each other by some strange fraction like say Fin by Fs was say 129 by 1024. Okay. So anyway, it's relatively prime to 1024. So this is a frequency in the range of Fs by 10. Alright. And if you took the outputs sequence now, it would be periodic and blah blah blah. The question now is, how on earth do we get, this has to be one signal source and this has to be another signal source, correct? And if you take two arbitrary signal sources, what does this relationship imply? This relationship implies that in 1024 cycles of Fs, there are exactly 129 cycles of Fin. So if I took two arbitrary function generators, the kind of stuff that you have seen in your undergraduate lab, okay, you have a dial which sets the frequency, isn't it? So as a simpleton, what I would do would be to set this to 129 hertz and Fs to 124 hertz. And so what do you think is the problem with this situation? When you have two periodic sources, alright, two independent periodic sources, even though they are both nominally of some frequency, what happens in practice? So you see that these are two, there's always random noise, and even though you manage to set the two exactly to the correct frequencies in the beginning, they will drift away with relative to each other as a function of time. A classic example is the setting up of watches, right? You synchronize your watch with, say, some standard or maybe with your neighbor's watch, say today. You certainly don't expect that if you come back here to this class, a week later, that both of them will be showing exactly the same time. And the reason is that, of course, it could be that the period of oscillation of the oscillator inside your clock is slightly different from that of your neighbor's clock. But even if it were the same, to begin with, over time there is noise and temperature changes daily over time and so on. So these things all affect the frequency of oscillation of these two independent sources, correct? And they will not be in sync after a period of time. So the same thing can be expected for any two independent clock sources. So even if this was somehow enforced at the beginning, as time builds up, the two of them will eventually get out of sync, so that this relationship will not be valid anymore. So you wanted 129 cycles of Fn in 1024 cycles of Fs, and clearly that is not. Is that clear to everybody? Okay. So it turns out, however, that it is possible to. So what did we just say? We said that if Fs and Fin were two independent clock sources or signal sources, the two frequencies cannot be related to each other by this number over all time, because eventually there will be drift, and that is happening because these are two independent sources. So what is the obvious solution? You make one dependent on the other. So it turns out that you can understand this. So you can use a phase lock loop to make the two of them, the two sources, to be in sync, these two clock sources, such that they follow this. And the basic idea is to make one dependent on the other. And if you buy high-end signal generators today, you will find that you can connect one box up to the other box, and the two of them will talk to each other and figure out, whatever it is they need to do to make sure that their frequencies are set in this precise manner, or whatever manner you choose, for all time. So, the question being asked is, this whole setup is only required, this frequency being, some magic number times Fs, is only required while testing the sample and hold. Okay. The question is, when are we ever going to test sample and holds in the lab in isolation? It's all likely to be a front end of an A to D converter, right? So all the discussion that I had yesterday and today will hold without any change to whole A to D converters as such, because all that follows once you have the sample and hold is a quantizer, which is again simply taking this discrete time sequence and giving you another discrete time sequence. So the discussion that we have today with respect to FFT's choice of input frequency, okay, frequency bins, all this stuff holds without any change when we talk about A to D converter testing. I'm not going to talk about it at that point. I'll just gloss over it simply because I've discussed it in sufficient detail here. Does that make sense? So this kind of testing is often called synchronous testing. Well, okay. What he asked was, are we ever going to be testing a sample and hold in isolation? Right? Because we understand that sample and hold is just what do you call a front end to an A to D converter, to a quantizer. Okay? So it is not likely that we will be designing isolated sample and holds and testing them. It will always be, a part of an A to D converter. So, and the next question he asked was, if we are not going to be testing sample and holds in isolation, why bother about this whole thing at all? Okay? And the answer to that is that we are not going to, yes, we are not going to be testing sample and holds in isolation. However, we are going to be testing whole A to D converters themselves. And where the output signal is a discrete time sequence and the input signal is a continuous time input. So the same discussion, how you choose the input frequency, how you choose the clock, and the notion of record length and all this will hold with respect to a full A to D converter also. So, this is called synchronous testing, just simply because the input source and the clock source are synchronous, in the sense that capital M periods of the sampling clock, okay, will be enough to exactly fit M periods of the input sine wave. So if you do the synchronous testing, okay, which is what I have done here, this is an example of, I have taken a sine wave of amplitude 1, so it is of the form, I think, the input signal x of t is sine 2 pi f in times t, and it is sampled at a rate fs, and f in by fs happens to be equal to 129 by 1024. That's how I have chosen my Fn. So when I sample this continuous time sine wave with at a rate Fs, where Fn and Fs are related by this rational number, I will get a periodic discrete time sequence. And what is the record length? This is the record length. So when I take the discrete time, compute the coefficients of the discrete time Fourier series, how many coefficients will I get? 1024 coefficients, and I plotted on the y-axis the log magnitude of these coefficients. So this is the 20 log mod A sub m, and you can see these are the so-called bin numbers. And as we discussed yesterday, there must be 1024 bins, and as we also discussed yesterday, there must be, magnitude must be an even function, so one half of the stuff must be symmetric about the other half. So for example, here, this seems to be the center of symmetry, alright, and this therefore must be, which bin must this be? This must be the 129th bin, okay, and this must be the 129th bin from the left side. So this distance and this distance must be the same. And please note that ideally what were you expecting? You were taking a pure sine wave and sampling it to get a discrete time sequence, which is now also a pure sine wave. So what were you expecting when you compute the discrete Fourier series? So there's only one input discrete time sinusoid, right? So the components, Fourier components at all other bins must be 0. So here you see that the input is there, right? But unfortunately we see that all the other coefficients are not really 0. So ideally, if you plot the log of the coefficients, then we should expect only one single tone, and all of them must be 0. So when you take the log of 0, you must get minus infinity dB. But please note that you are dealing with a finite precision machine, right? So even though you have a perfect sine wave, it is rounded off to 32 bits or precision there is. So this is basically noise. So the Fourier components of the real sine wave are not exactly, it's not exactly a pure sine wave, it is a very, very pure sine wave with some round off noise because of finite machine precision. So this is happening because of that. that. Okay. At any rate, you can see that this is 300 dB below the input tone, and 300 dB is a lot of dB. It is 10 to the power minus 15 or so. You understand? So this is what happens. This is what you would expect. Okay. So I think the best way to learn all this is to simply do it, and this takes 2 minutes on MATLAB. Okay. The fact that this is even though I put a an amplitude of 1, okay, you would expect 1 here, right? If you expand it as a Fourier series, but it turns out that there are normalizing factors in computing the FFT, all right? And in most cases, what happens is, you know the amplitude that you put in. So if you find that there is, for example, you found that there was a harmonic somewhere around here, okay? The absolute numbers do not need to bother you. All that you care about is how much the harmonic is below from the fundamental tone, right? So ratiometric measurements, all that matter. So in most cases, the absolute value of the scale usually doesn't count. And to make things cleaner and to prevent having people making mistakes from subtraction, you can simply normalize with respect to the peak. You just simply subtract off 50 dB from here, and the peak tone will be at 50. And all the other tones can be simply read off from the graph. This corresponds to, since these are strictly these are all bin numbers, but in principle this can also be mapped onto a frequency axis. So this corresponds to Fs by 2, and this will correspond to 129 by 1024 times Fs, which is approximately about Fs by 10. Now everything seems fine and clean when Fin by Fs is exactly 129 by 1024. So what is the obvious question? Hey, what happens if it is not 129 but 129.001? Okay, so what happens, for example, Fin is Fs times 129.01 by 1024. So I didn't tell you that it is, in fact, I tried to con you by telling you that it is actually, in fact, the input is 129 by 1024 times Fs, but whereas it is actually 129.01 by 1024 times Fs. You understand? And I gave you the samples, and like all obedient students, you would go and compute the coefficients of the discrete Fourier series. And this is in principle, as I keep saying, it is the best to do synchronous sampling, where you have two boxes which talk to each other and adjust their frequency such that the frequency relationship is a nice proper rational number. But in some cases, especially when you don't have any money, you can't afford to buy the expensive boxes which are capable of talking to each other. So you have to do with two boxes which don't talk to each other, in which case all that you can expect is that the frequencies are approximately 1029 by say 124 in this example, but in practice, the number might be slightly off, and one example of a number which is slightly off from 129 is 129.0, right? So when I did that, this is what I get. Okay, so this corresponds to Fin is 129 by 1024 Fs, correct? The red curve here corresponds to Fin being equal to 129.01 by 1024 Fs, and this corresponds to Fin being equal to 129.001 divided by 1024 times. You understand? So what do you notice? So let me zoom in. So this is the correct Fin. This is Fin times 129.01 Fs by 1024. This is 129.001 Fs by 1024. So what all do you notice from these two pictures? From these three curves rather? One obvious thing is that as it gets close to 129, you see that the discrete Fourier series coefficients, the pattern seems to be resembling or tending to go towards what you would get for the ideal case. That makes sense. Okay. But, and in any case, for information's sake, when you see this happening, okay, this is often called the Eiffel Tower effect. So, clearly, there is, things don't look as hunky-dory as they do with the right input frequency. One thing is that the bins which are all supposed to be zero, mind you, okay, you just have a pure input tone. The bins which are supposed to be all zero are now, what is happening? Earlier all the bins were 350 dB or so below the fundamental. Now what are you looking at? So, you can see that the bins are definitely not very small anymore, okay, and they are only 40 or 50 dB smaller, and the difference seems to be reducing as the frequency becomes closer and closer to 129, the right value, 129 fs by 1024. So, can somebody give me intuition about what is happening here? If the DFT bins are filled up, it appears as if there is energy at not just one tone but a whole bunch of other tones. Okay? Which certainly is not true. You know that you're putting in only a single sine wave. If I found the proper record length, what my friend here is pointing out is that instead of taking a record length of 1024, if I had taken in this case, if I had taken a record length of 1024 times 100, then there will be exactly an integral number of cycles of f in 1024 100 cycles of fs. Sure, I buy that. But the question is not what do you do to fix this problem, but why is the problem happening in the first place? Only when you understand why the problem is happening, then you will be able to fix it, isn't it? So, in both these cases, right, the signal is not periodic, correct? And what we are doing is basically, let me just go back to this picture here. So, let me give you a quick refresher of our discrete Fourier series. So, if I had a finite length sequence, S of n with a sequence length m, what is the Fourier transform of this sequence? S of omega is nothing but sigma k 0 to infinity, which is the same as 0 to m minus 1, S of n e to the minus j omega k. Correct? So, and what is the discrete Fourier series of this of S of n? This is the discrete Fourier transform. Thank you. S of k e to the minus j omega k. Correct? What is the, if I decompose this as when I compute the discrete Fourier series, what am I assuming? So, whenever I compute a discrete Fourier series, what I am assuming is that this S of k is one period of a periodic waveform. Okay? So, when I compute the discrete Fourier series, I have simply expressed this will be S of k e to the minus j 2 pi by m times, let me see, 0 to m minus 1. Right? So, this gives me the mth coefficient of the, let me call this S1. of m. Correct? So to find the mth coefficient of the discrete Fourier series of this sequence S of n, I know that the sequence has got length m minus 1. So I can make a discrete periodic sequence by making periodic extensions of the sequence. Once I have a periodic sequence, it's straightforward to compute the coefficients of that discrete Fourier series. And they are simply obtained by taking the sequence and multiplying it by every sine wave possible, right? And since you are in discrete time, there are only m sine waves possible, okay? So you have m coefficients. So do you see any relationship between this, so you can see that the discrete Fourier series is nothing but samples of the Fourier transform, okay? And as the sequence length becomes larger and larger, and eventually as m tends to infinity, the discrete Fourier series coefficients or the Fourier transform will become the same. Now, in practice, you don't have a signal which is fixed in length. Okay, it's for example, when you put in an input sine wave, what you're doing is you have the output sequence is an infinite sequence because it's periodic with time. Okay, what are you doing? You're taking a record of length m samples. Okay, so what you're doing, so in practice, what you're doing is you're taking an infinite length sequence okay, and you're only considering m points, and then so chopping, retaining only m points. So if I have this infinite length sequence, for example, this is some sequence, but I only retain, say, these points, okay, what is it equivalent to? So it is equivalent to taking S of n and multiplying it by a rectangular window W of n, which is 1 for n being equal to 0 to n being equal to m minus 1. Does that make sense? See, regardless of what the input frequency is, this is what I am doing. I cunningly chose the input frequency to be some magic number, okay, for some reason which will become obvious little down the road. But you already know that we chose it to make sure that we'll be able to compute the output sequence will be a periodic sequence. This will give us another way of looking at the same thing, and more importantly, tell us what happens when the input doesn't, is not that magic number. So you can think of taking a record m or m samples or 1024 samples of the output of the sample and hold as taking the signal S of n, which is the complete sequence coming out of the sample and hold, right, and multiplying it by a window function W of n, which is simply 0 everywhere except for n ranging from 0 to m minus 1. Correct? Is this clear? So we are taking, okay. So what do you think is the Fourier transform of this chap? The Fourier transform of this record is simply the Fourier transform of S of n convolved with the Fourier transform of the window. Okay, so the discrete Fourier transform, let me call this P of n. So P of omega, which is the discrete Fourier transform of P of n, is nothing but the convolution of S of omega with the Fourier transform, discrete Fourier transform of the window function. Okay. So if you have so let's find the window function, the Fourier transform of the window function. It's 1 minus e to the minus j omega m divided by 1 minus e to the minus j omega, which is e to the minus j omega times m minus 1 by 2 times sine of omega m by 2 divided by sine omega by 2. Okay. Intuitively, can you tell me why this term makes sense? That this represents, this m minus 1 by 2 samples represents the average delay of the signal, right? So if I chose my origin, for example, to be here, then that term would go to 0. E to the minus j omega n is basically a delay of n samples, isn't it? So what is the average delay here? If this was 0, the average delay is 1, 2, m minus 1 by 2 samples. Okay, so that's why it makes sense. So, and what is, so if I put in a pure sine wave, okay, what is the spectrum of, what is S of omega for a pure sine wave, regardless of what frequency it is? It is it's an impulse, correct? So S of omega is basically an impulse, it's a bunch, it's two impulses like this, correct? And the window function, omega, W of omega is something like this, which goes to 0 at what all frequencies? It goes to 0 at multiples of 2 pi by m, right? So this is 2 pi by m times 2 and so on. So if this lies exactly at 2 pi by m times m, which is what we had concluded yesterday, right? We said we want to choose the input to be related to the sampling rate by a fraction small m by capital M, which means that in discrete time it will appear as 2 pi times small m by capital M. Is that clear? So, what is the Fourier transform of S of omega, S of n times W of n? It is this chap convolved with this guy. Is that clear? Okay. So, if I convolve these two, what do you think will happen? It will shift. So, at 2 pi by m times m, it will be like this, and then so all these red dots, circles, represent multiples of 2 pi by m. And I will not draw the left half because it's simply it's what you call even symmetric, magnitude is even symmetric. This is just the magnitude. Does it make sense? Okay. So this is the discrete Fourier transform of S of n times W of n. Okay. What is the discrete Fourier series? It is just the samples of this at 2 pi by m. So when you sample this black guy at 2 pi by m, what do you get? You just get only the red circles. Correct? So the black guy is the discrete Fourier transform Okay, and these correspond to the bins of the discrete Fourier series. This is a roundabout way of saying that if I chose the input to be rationally related to the clock, then I would get only, if I expand that, the output, the sampled output would be periodic, which means it follows that when I expand that as a discrete Fourier series, I will get only one peak. Okay. Now, but the reason for going about this in a roundabout way is to impress on you the implications of not choosing f in the correct way. So, what do you think will happen if okay. So, if Fn is not exactly 2 pi m by m, what do you think will happen? So, what will happen is that this chap, okay, the sink remains as it is. However, the input tone is not sitting at 2 pi m by capital M. So, this is slightly off center, right? Okay, and you are sampling now at these points which are slightly off, and so on. Okay, so this is input not of the form m by m times Fs. Okay, does this make sense? And when you plot the DFS coefficient, discrete Fourier series coefficients, it's simply going to join all the red points. So that's why you see the Eiffel Tower. And clearly, the closer the input tone gets to 2 pi times m by m, the closer you will get to the 0. So you will so the Eiffel Tower height will become smaller and smaller. Does this make sense to all of you? So that explains this. You understand? And another thing that you see is that what is the difference between these two? Look at this. These two curves seem to be parallel. And the difference between the two is 20 dB. So the difference between these two curves is 20 dB, right? And that is coming because the error in frequency is 10 times smaller. You understand? Actually, I think I will stop now. I will continue on. Please think about this. I will continue on.